It's a great pleasure to introduce two distinguished speakers in this session. One of them is my close colleague and collaborator, Mark Verbrugge, who's director of the Chemical Sciences and Materials Systems Lab at GM. And in addition to his heavy managerial responsibilities, he's somehow able to run a science operation on the side and has a number of distinguished publications in the electrochemistry field. He's also a member of the National Academy of Engineering. We're very pleased to have him here to talk about our work jointly in the CRL and also other opportunities for industry collaborations, university collaborations in the automotive sector. And the second speaker will be Paul Wang, who's Deputy Director of the Center for Advanced Vehicular Systems. Is there another word after that? Center for Advanced Vehicular Systems at Mississippi State. He has, and his colleague Mark Horstemeyer have a big operation in computational materials research for the automotive industry, and he'll be sharing his perspectives from the university side. So I think Mark's going to speak first. And plug his laptop
And I have a movie to show too, if we could do the plug and play on it.
You probably have to export your screen.
Like trying to put a workstation up here. Okay, thank you, Alan and Clyde, for the introductions. And as Alan mentioned, I'm going to talk today about the title here, Advanced Automotive Materials, the New DNA of Personal Mobility, and some of the figures that you see down below are representatives of the work that we're doing actually in GM R&D. The conventional in-cylinder, actually HCCI combustion, a special form of combustion that we're looking at to advance engines. Some teamwork with NASA on robotics for manufacturing primarily. The Volt battery pack, and then a movie I'll show on the very last slide that should be amusing, I think, if nothing else. So outline is shown here. I'm going to talk a little bit about GM and GM R&D, some of the automotive challenges and potential paths forward. These would be sort of the listing of needs, if you will. And then more specific to materials needs there that I think will be of help here. And in my own particular case, I've dealt a lot in my research with both lightweight materials and energy storage solutions. I'm going to focus on those for today, and I think those are actually critical growth areas for the automotive industry as well. And I'd like to then close with the Brown General Motors Collaborative Research Laboratory. So real quick with regard to General Motors, goes back to the turn of the century. The 2011 was about a 5% return on sales year if you look at it for a $160 billion business, $150 billion, and employs about 200,000 people. The history of GM R&D, it's one of the first, actually, automotive research laboratory. And it used to be more or less centralized in Michigan, and now it's very much a global network. You can see that here in terms of the overall makeup of our R&D network. And the Collaborative Research Laboratories is a big part of that. One of the things I would tend to say, automotive is an extremely competitive business. In the best of times, the best companies are making about 5% return on sales, yet you're talking about structural costs and revenues that are well over 100 billion. So if there's a downturn in the economy, it gets tense. And for that reason, it's been considered to be a very tough company to be in. And one way I look at that as far as how to get research done is you have a bit of a junkyard dog mentality. You're willing to collaborate with anybody, and it's just a lot faster way to get work done and get research done. So at any rate, with that in mind, some of the brief history going back to the start of the vehicle. And the reason to me this slide is useful is, why do cars look like they do today? And that is actually a profound question, because you'll see, again, if I get a chance to show the movie at the end, I'm not sure cars are going to look like that in the future. And in some sense, you can trace it back to the horse and buggy. And the LaSalle coming out in about 1927 is often viewed as one of the first modern day vehicles. So you want to buy a vehicle, typically if you're in the United States, you want to buy one that has 4 to 5 passenger capability, and you tow that mass all around with you, and it's covered and it has all the attributes that you'd want to have out of a vehicle today. So if you then trace yourself back up into about the 1950s, you see that same basic attribute. And styling was king at that point in time. You now had model years coming out that tended to rule the day, and the models were fairly differentiated. However, there are about 200,000 to 300,000 units per model, and that's kind of important, and I'll come back to that. So then if you advance forward from there, we had 2 relatively large shocks that changed the industry. So one was a safety focus, and that now manifests itself in airbags and basically extremely safe vehicles, relatively speaking. And then there's the oil shock in the 1970s, and a lot of folks here won't have been around at that point in time to remember that. But I can remember having to park our car at the gas station in line, and then you go down there, walk down there, and you know, your dad gave you about 25 cents, and you could fill up the car for him, and then he'd come pick it up later. But at any rate, so the progress has been fairly profound since that time. There are greatly reduced emissions, and this is important, and I will touch on it here and probably won't mention it again, but there is this extended range electric vehicle concept. The Chevy Volt has that embodiment. And one of the things to keep in mind is that the emissions between cities, which you would drive the internal combustion when you go between cities, because you got about 40 miles of electric range in that vehicle, is pretty much negligible. It's hard to measure some of the regulated emissions at this point in time. That tends to set the regulations. So they're extremely clean, especially after they've gone through light off and are driving on the highway. Fuel economy for cars has increased about 180%, nearly 200% for trucks since the 1960s, about 100%. Fatal crashes have gone down by quite a bit then, obviously, as well. And affordability in terms of content that you get has gone down actually as well. It's not realized by many people. So one of the problems that we had in like the 1980s and 1990s, we got very good at making these 200,000 to 300,000 unit vehicles, but we badged them differently, and they all look kind of the same. And so you tended to get more or less a boring styling approach, if you will. And so then if you come up to really the year 2000, what happened a lot there, a lot of emphasis on fuel efficiency and hybridization, which I'm going to talk about, electrification of the vehicle. But the other thing that happened was this sort of pervasive styling change. And so now it's very common to have about 50,000 units per model. That places a great deal of emphasis on agility in manufacturing. So when you have forming processes, you want to be able to use the same die and presses. You can't replicate these things. A body shop costs about $1 billion in an automotive assembly plant. And so you got to be able to stamp all these different parts. You have to have quick change of tools, and you have to have basically very robust, in that sense, simulation codes so that you know how to do stamping and not have problems with regard to agility and making different parts. So now coming on to the next part of the talk that I think is quite important, some of the automotive needs. And one of the most important things is just to keep in mind, because you're going to see it pervasive, is sustainability. That's going to be probably one of the biggest things that we face. We don't really see it right now. You don't see it, you don't feel it, but it's probably going to be out there quite soon for us. So I'm going to walk down this argument to say why should we care about sustainability. If you plot any commodity pretty much, and cars, and this is what we're talking about here, ownership of cars per 1,000 people on the ordinate, and then we're plotting that against per capita GDP, and you see some countries like Australia that have a whole lot of raw materials are way out here at about $60,000 GDP US per citizen, but basically as you get up in your GDP, you're going to be buying more things. That's true of fuel as well. Now, there's also a change in demographic. Look at this chart for just a minute. Those that I've colored in red, that are closer towards the origin, are emerging economies. They're going to grow, without a doubt. How do you know that? Well, they're going to come up this GDP curve. That's going to happen. So those that are in green are more or less at the presumably sustainable state, if you will, or the developed nations. So take a look at this bar chart, and you can see it. China sold more vehicles in China last year than in, for example, the United States and Europe. And yet it's still growing. You can see that the growth it's a developing country. It's still going up in vehicle ownership. Europe is going down or holding steady. The same is true of the United States. Same is true of Japan. Japan has a negative population growth. Brazil is a developing nation. And one of the things you find when you look at these things is the vehicle sales in the emerging market right now are about the same as the vehicle sales in the developed market, if you just integrate all these things out. About 3 years ago was the first time General Motors actually sold more vehicles outside of the United States than they sold inside the United States, and that trend will likely continue. And you can see the growth of China. It's amazing. If you look at it versus the year 2000, it's almost 1,000% growth in vehicle ownership. You know, we can expect to see then this about 12% growth rate in automotive today, just based on these developing markets increasing in vehicle ownership. So, you know, this is why I was going to this current DNA and new DNA in the talk. The current DNA, we're energized by petroleum. Likely that's going to have to change. We've already had people, and I don't have enough time to show all the slides here, but people talk about from oil companies, the first time was about 5 years ago, saying we're past the point where our known reserves can supply all of the known demands. So there's a gap at that point. People thought that tipping point would be a rather dramatic change for energy security. In some sense it is, but for the most part, people don't think about that every day. But we're going to see much more reliance on alternative fuels in the future. In the past, we were powered mechanically. As you go to more electrified vehicles, you'll have other power sources come on and other couplings or transmissions, so electric coupling, if you will. The next thing is standalone. I'm going to show on the next slide connected vehicles, but one of the things we need to address for, in particular, congestion, which is a large problem with our emissions as well, is vehicles got to talk to each other. And the other thing is, what's even harder, vehicles got to talk to the infrastructure. Well, the real question to ask is, will vehicles at one point in time be safer driven by just the vehicle than for the owner driving the vehicle? And there was a DARPA Grand Challenge. GM entered that with Carnegie Mellon, and we had the winning vehicle, and it was a Suburban, and it looked like all kinds of claptrap around the vehicle that had all kinds of sensors and LiDAR and everything else, but it could drive a course. And the course was kind of funny. They had even changed the course from the original map, and so the vehicle still had to drive it when a stop sign was one place and now is no longer there. And the vehicles can do that. We can do that today. They're incredibly expensive, and they're a bit slow, but nonetheless, you can actually drive autonomously today. That isn't a question. So the question will be then total dependence on the driver versus autonomous driving. And then the last thing I would just say, and I'd mentioned it earlier, sizing the vehicle appropriately. You don't always need to carry around enough vehicle mass to house 3 or 4 people, especially on daily commutes. And so that likely will change in the future. And I'll give a potential vision of that. So I'll focus on energy and emissions. I mentioned these other challenges previously, and of course these are going to be posted, the slides, for folks who want to look at them later. But at any rate, with regard to conventional vehicles today that you see on the road, we have 2 types that are available, and I'll make a brief comparison of the 2 right now that might be solutions to our immediate future energy challenges. The Volt is one of them. I think it's well known by most. The general architecture of the vehicle is shown here. And it has this attribute of having, I should say, stop on that for a minute, that it has about 35 in cold weather, about 45 actually in hot weather as far as miles you can drive electrically. No matter what you do during that time, it will drive electrically, even if you put your accelerator pedal to the floor. That differentiates it from a plug-in hybrid. A plug-in hybrid is not a full-function EV before it drives out its battery pack state of charge. Once you drive off that 35 to 40 miles, then the vehicle will act like a charge-sustaining hybrid, much like a conventional hybrid, if you will. It has still a fairly large battery because a lot of reserve is left, about 25% of the pack capacity. It's a 16 kilowatt-hour pack. And so the combined range is somewhere near 400 miles, depending on how it's actually driven. So we've announced, and I don't know, see if I think Tony's still here. Tony, I actually put A123 on my slide. You didn't put GM on your slide. It was one of the collaborators. But anyway, we've announced that A123 will be supplying the battery pack for our small battery electric vehicle that's coming out. It's shown here. It's off of our Chevy Spark platform, much like the Chevy Volt is off of the Chevy Cruze platform. Some different electrode materials are shown here, and I won't dwell on this more other than to say there's a lot of work to be done in that area, obviously, to reduce cost and improve performance of electrode materials. So now, if the batteries don't go far enough in terms of reducing cost, particularly for a pure electric vehicle, the batteries are very expensive in that particular case, the question arises, will fuel cell costs come down, essentially? Because at the end of the day, what's really important to consider, as you can see on the lower part of this slide, is that the only vehicle that can provide 0 emissions off the vehicle, not off the grid. You can have some emissions where you generate your energy, but on the vehicle, 350 miles of range, and approximately a 3-minute fueling time, much like we have today. There's only one vehicle type that we know that can do that, and that's a fuel cell. Of course, the problem is fuel cells are extremely expensive. So cost reduction and infrastructure deployment, which will likely follow the cost reduction, would be the two most pressing concerns there. So some of the remaining challenges are shown here. Actually, the balance of plant is very expensive in a fuel cell. You got a lot of things running, pumps and everything else that make the critter go. The hydrogen storage system, people often forget, is very expensive. We did a fair amount of work ourselves on solid-state hydrogen storage, and there's a lot of interesting material science there, but it just looks extremely difficult to ever store as much hydrogen in a solid-state material as you can get by very, very high pressure carbon fiber tanks, and that's really what's used today, but they're very expensive. Carbon fiber isn't used pervasively as a structural material because it is so expensive, so you're more or less pushing that expense back onto the fuel tank in that particular case. There's an analogous problem with natural gas tanks as well. And then last, some of the other things you might not think about, it turns out bipolar plates are very expensive. They're made out of stainless steel. You can kind of think of a John DeLorean fuel cell engine. So it's a whole lot of stainless steel that goes in there. People are looking at non-ferritic, low-cost stainless steels for that purpose. But the corrosion environment is very tough. You've got hot oxygen, it's moist, and it's on the oxygen cathode, and that's a very corrosive environment. And then some of the things like steel processing and welding. Actually, the longest line length of welding that GM has probably ever done would be in the fuel cell bipolar plate joining. So these are enormous challenges to get the stack-up fit and architecture correct for eventual widespread application. So the next thing I'd like to talk about briefly is about vehicle light weighting. You get about a 6% improvement in fuel economy for every 10% decrease in mass. And some of the other ways that you can look at this are listed there, but it's a significant lever to pull in terms of trying to reduce fuel consumption. If you look here at this table, you can see some of the materials and the approximate reduction that you can have relative to low carbon steel. Now, actually, these are somewhat usage dependent. Are you talking extrusions or castings or what have you? But the approximation is shown there, and the basic point is most of our car today is made out of low carbon steel, and there's an opportunity there then to reduce mass. The obvious problem is that these materials tend to cost more. They're typically looked at as high value materials in automotive. So if you look at material trends over the past 20 to 30 years, you can see that here, that we had a lot more low carbon steels in the past, and now we're moving more into polymer composites, about nearly 10% of the vehicle. It's mostly thermoplastic olefins and other plastics that are used as closeouts and fascias. Aluminum is about 10% on a vehicle as well, primarily in the cast engines. Nowadays, because the way vehicle architectures are set up, you have most of your mass over your front where your engine is, so you want to lightweight there, because otherwise you have a front-heavy vehicle. And so you pay a premium to lightweight up near the front of the vehicle. Likewise, you try to lightweight at the top of the vehicle and your unsprung mass. But the aluminum has made it in there for the cast engine parts in particular. You see very few new engines coming out that aren't cast in aluminum. And the question will be, can magnesium be made strong enough in terms of creep strength and also corrosion resistance to be replacing aluminum in the future? Corvette is sort of a poster child in our case for lightweighting for a different reason than fuel economy. It has to do with about 3.5 seconds for 0 to 60 on that vehicle. So there you see for rotating parts, titanium is often used to not limit our horsepower on those systems. Magnesium near top of vehicle for the magnesium roof shown there. And then carbon fiber floor pan. Actually, there's a balsa floor pan that we have in other systems as well. And then actually the Corvette, the way it's structured is sort of unique. It's to the industry. It's got these frame rails that run from front to back, and they're pinned by the bumpers. It's the only vehicle that's actually designed like that. And then through the center section is a stamped aluminum part that actually binds the two frame rails together. So the longest frame rails in the industry are actually on the Corvette for that aluminum frame, longest hydroformed frame rails. There is a project we've done through USAMP. One of the things we've come to realize is nature has given us a whole bunch of materials, and so you want to kind of put the right material at the right place. And you can think of not just topology optimization for load paths, which we all have done for many years, and it's still a very complicated subject, but also materials optimization at the same time. And ideally what you want to do, of course, is couple materials optimization and topology optimization. So here you can see you have an advanced high-strength steel passenger compartment that tends to protect the passenger. And then you have front A-pillar forward, so that front engine compartment region is dominantly magnesium. And then the floor pan, because of its nature of a large flat surface and fairly massive, is a composite floor pan, and it tends to make more for an optimized vehicle system. I won't say more about it other than to say recycling is a big part of the automotive industry today. It has in the past, but it gets a whole lot of attention now, as it should. And so we strive very much to have recyclable parts in all systems. This is now coming to this whole notion of reinventing the vehicle. And I have a 3-minute video, but let me ask, how much time do I have now? Because I want to know whether to show this. Well, I want to do the Brown CRL afterwards, so I got about 5 minutes there. Okay, so let's hope that this runs. I don't know, though, that I have the sound plugged in. That's one thing I'm worried about. All right. Here goes the experiment. There we go. So the basic notion is think about how you might reinvent transportation around this idea. Vehicles compete for their electrical connected. They're electrically driven, and therefore you can actually do much more And one of the things that I'll just teach you with, and I'll say a little bit more about it, from a material science point of view, what would you make these vehicles? We actually throw some of these vehicles in the lab and think back. Driven vehicles, and they have that attribute then of being both electric and networked. And as I was trying to tease you with the question, the chief engineer for this project and myself wrote a paper where we said, well, okay, if you did that, how would you build a vehicle? How would you manufacture it, and what kind of materials would you use? And the short answer would be you'd probably put in a lot more magnesium structure, and you'd use a lot more thermoplastic olefin closeouts, because then you get very lightweight. You have an electric drivetrain. You don't want to tax that drivetrain any more than you have to as far as the energy storage device goes on size. So I'm going to talk just a little bit about a case history of some work that we've done in collaborative research laboratories with Brown now. So in the context of General Motors, what we think of as a collaborative research laboratory is basically a strategic partnership, if you will. We make it in processes or steps, if you will, of 5-year commitments. We're actually on our 3rd phase with Brown University in this regard. we typically have a group of professors that work together with a group of researchers, and that collaboration is sort of the key piece of it. Without that, it all kind of falls apart. If it's 4 or 5 professors doing work and you're accepting the work and saying, okay, that's fine, then you don't have a collaboration at that point in time, and it's one way. So GM fully funds it. We encourage sabbaticals and student interns and visits. It's something that's quite important to us. And we define basically the roadmaps, if you will, or tasks that we want to close on jointly together. Basic structure for our collaborative research laboratories is shown here. It's pretty much what you'd expect. We have directors from both sides, and it's basically a joint industry university endeavor. And in this particular case with the Brown GM Collaborative Research Laboratory, as shown here, it's focused on computational materials research, certainly appropriate for this forum. And we have a saying we often use, atoms to autos, and the basic notion is go from calculations that are rather basic in nature, from say density functional theory to atomistics, and then work your way up through maybe single crystal plasticity, finite element calculations, and into vehicle parts. And we have a couple examples that I'm not going to talk about precisely here today, but we've actually done that exchange of length scales. Now, I don't mean to say that the code that we run in automotive for design, that is LS Dyna in GM's case, others use CATIA or other finite element solvers, we don't put atomistics in those codes, but we can inform our constitutive relations that are used in those codes by what we learn from some of these smaller length scale endeavors. And that's where the linkage comes in, and it actually becomes very, very concrete in many examples. The posters out there did a real nice job, and so I'm only going to show very quickly 3 things. In this case, we're looking at solute strengthening, and it's interesting where the solutes end up. Actually, if you have an interface between the tension and compression side, they don't always end up on the same side, and it has to do with size of, and as well as electronic effects in these systems. And then coming up from things like electron structure calculations in the past to here, the influence of grains and crystal structure become important, especially for single grain plasticity. And then as we move up in length scales, we actually get into treating stress-strain relationships, and these can feed into our vehicle simulation models. And there's some examples here of electron backscatter diffraction experiments, and we have a nice setup that we've used and actually learned a lot from Clyde and Brown in this area on how to do in situ electron backscatter diffraction under tension and compression, and then be able to track it, and then we can inform our models with that kind of information. The CRL structure for our next 5 years, what we're working on right now for the past year, we've been doing this, we sort of split out. We realized that with all this emphasis on energy storage in automotive, and especially as we go to these higher energy density materials, they tend to expand and contract quite a bit. The conventional materials that are used in batteries today expand between 5 and 10% each on the electrodes. As we go forward to, say, silicon-enhanced negative electrodes, and maybe even sulfur or other positive electrodes, now we're talking about expansions in the order of 100%. And so you have to kind of do 2 things at that point in time. You got to get the particles extremely small so that surface effects become important and tend to hold the material together. And you've got to terminate to the electrolyte with a chemically stable layer, say a carbonaceous layer, for example, that doesn't have chemical degradation reactions with the electrolyte. And these are the kind of things we're trying to get a handle on computationally. And we're also at the same time doing some experiments. Primarily the experiments are done, well, actually at Brown and at GM in this particular case. So maybe just a helpful concept. This is sort of a Boston Consulting view of how to look at collaboration, but the basic notion, well, some things are kind of obvious, I should say. You just never want to end up down in the lower right, so that's not a good thing to talk to management about. And you want your silver bullets, if you will, then would be things that are absolutely important and that you don't have strength in, but you don't need much strength to actually grow. So the candidates for a virtual business are sort of in this central region where you're not really sure where things are going, and yet at the same time you feel like you need to be a player there, and you can basically buy down your risk and expand your resources if you then create a collaborative research laboratory, and that's what we've done. And so now, as far as the automation goes, it kind of shows the notion that over time when things go well, it's hard to tell who's the researcher from GM and who's the doing the contributions from the PhD students as well as the professors. It tends to be one entity at that point in time, and it's most successful at that point in time. So in my view, what really makes a CRL, Collaborative Research Laboratory, successful, elements of collaboration are, I think, pretty obvious, but they're nonetheless helpful to state and be concrete about. Trust is obviously a really big issue. We do tend to share a lot of information, and trust comes with that, and you build that up over time. Those are about relationships. Problem selection typically comes from industry, at least for the grand problem, if you will, and then parsing it further to find out, well, what are the really big rocks in the road to actually solve that grander problem? That's done jointly, and oftentimes the professors will be best at clarifying those things. Need a champion on both sides. Alan and I are sort of the co-directors of the CRL, and so we're the champions in that respect and have worked hard to keep this thing going well. And then, great people. Obviously, that makes great projects and great work go. Then the second thing is recognize the value of accomplishments. I put them here for the last phase of our CRL, that is 2005 to 2010 timeframe. And I picked out 3 figures, but we had about 62 publications. These internal reports are listed that then tie back into actually GM internal initiatives. And they're broken down into different categories. That was mostly associated with lightweight materials. We started a little bit on batteries toward the very end of that phase. Presentations mostly invited, about 41, and there are other key metrics that are important. I'm not going to put them down here, but graduation of students and thesis written and things like that. But those are things that are important because it turns out when things go well, at the end of the day, you typically have things you can count, and it's important to recognize those things because it adds to the goal congruence for a collaborative research laboratory. So some closing thoughts then on the Materials Genome Initiative. I think everybody agrees some generic form of information sharing is important, and it's something we would like to do. There's always going to be the question of validation as well as verification of models. There have been examples in the past. Pacific Northwest Research Laboratories, I know, held some materials data in the past and made sure that it was in good shape, sort of like a Wikipedia, if you will. So my thought is, in terms of an MGI, we might have to actually dedicate some funds to some entity somewhere to make sure that this stuff is actually collected, can be disseminated, and the information is good. Somebody's scrubbing the information to make sure it's standing up to a certain level of integrity. And I think it's important to note, in terms of industry, it's going to be hard getting industry coming in. My tendency is to believe if you don't bring industry into these things, a lot of stuff will get done in the name of materials research, but I'm not sure how much is actually going to get out to help society. And so I think it really helps to have industry helping to drive these things. And you have to motivate companies. I'll throw out a name. Alcoa has depths of material properties on aluminum alloys, from what I understand. How are you going to energize Alcoa and GM in case of dual-phase steel to go and dig through all their archives and dig out that information and make it available? That's a cost. And so industry is usually worried about keeping those costs down. And so some incentivization is probably going to be needed there. And last, as I've mentioned on the CRLs, that may be a useful model where the government helps to, or the MGI initiative helps to identify and set up these CRLs so you have this industry university collaboration, and it's a real collaboration at that time, and very, very good work can get done. So with that, my summary is actually just a repetition of my outline, and that's all I have to say. Thank you.
Thanks, Mark. That was great. We can take a couple of questions while Paul sets up for the next presentation. All these reams of data that you guys have on dual-phase steels, do you sell?
No, we don't. No. It's more a matter of, these are, in dual-phase steel, for example, it's a case that was pre-digital age. It's still a lot out. I think the same is true of other material companies. So somebody has to actually go into these databases and get it out. I think that's more useful than repeating a lot of those tests.
Do you have any concerns about some kind of proprietary type of thing?
All the time.
Competitive, and you can't publish it?
Well, no, I mean, you do have to, when you go to a collaborative research lab, you pick out problems that tend to be enabling. And what happens is over time, as you build up trust, you sort of push that boundary back and have always more information. And that's the way I would argue any organization works. You end up, you get what you give. So you have to err on the side of giving sometimes, and if you have good trust and a good working relationship, it's never a problem. And it's never been a problem around. We haven't had one time, to my knowledge, where we ever said, oh my gosh, we published that, we shouldn't have done it. It's not happening. So I think if you invest time in true collaboration, then people understand that there's something sensitive, and it works quite well, is my experience.
We'll come back and a couple of questions.
Well, I probably have 1 minute, so I'm going to catch up. I'm very happy to be here from Mississippi State, and I'm not sure how many people has been visit the state of Mississippi. It's done way down the south. Anyway, today, thanks for Alan, I'm organized this particular talk with you, which behind me actually a fair amount of research group working on this, and I will just give you a few examples related to Material Genome Initiative. My partners, Mark Horsmeyer, chair professor at the same center. Just mention that the culture down the south from automotive environment is quite different with north. In the north here, Brown with General Motors, Northwestern with Ford, those kind of things. But if you look at here, we have Mercedes, BMW, Kia, Honda, Hyundai, Toyotas, and Nissan. And in fact, the center I'm situated right now actually was initiated because Nissan set up a plant at the state of Mississippi, and with the condition that the state Mississippi committed some sort of funding support the center. So that's kind of a relationship and culture we have there. Okay, I just want to briefly give you what we're doing down there with some sort of funding with different resources, and come to the with 3 different group of materials. And a lot of people previous talk mentioned about all those things. We group here one's lightweight materials, and okay, I got here. This one will work. Lightweight materials, which mainly will be aluminum, magnesium type. Especially we work with USM and Mark from GM people. So magnesium become a priority at this area. And we also work on steel metals, steel alloys in the sense of we have a few what you call the material suppliers or the steel making kind of plant like Seversol, Nucor down there. So we have research going on. And also the material, polymer materials will be broad enough cover synthetic and organic type. So synthetic, we have a typical composite and polymeric material. And the organic one, we also work on tissues, bios, and bio-inspired type area. So basically, it's physics-based material model in address the material. So the discipline really combined of mechanics and materials. So material science and mechanics work together, just what we have here. And emphasize lightweight, and eventually develop new material and math-based tools. And cradle to grave is the one we are trying to address. So we have this kind of system thinking, give the student and the researcher what is the process impact, the property and the structures. And that's what this relationship is. And we do have an education program in some sort of, so we take this outcome of the research and get into K-12 and from master PhD program. So our approach is look into the history effect, especially process structure product relationship. And also there's a cyber infrastructures in the university level, working with DOE and others, national laboratory. So we can contain some of the material database for the 3 material branch we talk about. And we also, not ignoring, but think it's very important that you have to do experiment. But we don't want to compete with, for example, large corporation. So we're doing very small scales. Scale sometimes small enough that coupon level to the SEM, TM level. So that's what we're talking about. And demonstration certainly will work with sponsorship and see how that can be correlated. And that's what the partners become very important to us. So this is the way we use in the cradle to grave. Actually, this is the one I work with, Mark Horstmeyer. We use aluminum as example to address how important the material history is, because the old car or new car, at the end of the day, they perform differently because a lot of aging effect. And certainly multi-scale in the hierarchical impact at different conditions provide different information will come into different levels. And that's the, we call it computational manufacturing design. And this is a typical multi-scale material model in the bridging effect. So you have electronics-wise, you have the interfacial energy, cohesive energy, and how that come along. Then you can get into the atomistic one, where I give you the mobility and then dislocation and so on for crystal plasticity. This is typical for metal form where we're doing this. And for the polymer, then you go into the molecule chain and way down there and way up there. And we have some little success MIT has quite a bit of work going on there. The cyber infrastructure is a very interesting one because 5 years ago, each researchers, if they leave the site, we can retain those information. But with this cybers, at least we can retain what the material data is, and also what is the model potentially already being developed, and put it right in there. So there's a quality check, and also pass on as accountability for each group that put into this cyber structures. And eventually, those engineering tools may be able to do the on-site web computing type dream about it. And here, just give you a magnesium overview. In fact, we work with USM, General Motors, and Ford people, look at the front end situations, how we address the sheet extruded, cast part. Can we analyze, use ICME techniques to address the structure part? And when you backward, you can get into the molecular dynamics and crystal plasticity, and all the way to the stress strain curve to analyze these structures. So there's a number of tasks we have. Start from high level way down to the certification and the simulation-based design optimization. And this is just typical, the yield surface of a typical magnesium, which incorporate twinning in there, and how the mathematical tool can develop with it. And we do have a sponsorship for this kind of work. Again, this is still a program. The interesting part is in our backyard, we have a twin roll caster with a sheet product. It's only 10 minutes driving away. And they've been working with us for the past number of years, 2 or 3 years. We try to understand what they're doing, as well as they try to show us what their need is. For example, a dual-phase alloy in the higher grade, and a trip alloy and what application is. So we start getting to not only the steel manufacturing making, but also looking to the process, what kind of software code, and how our multi-scale can help enlarge that existing software, which is we call metallurgical code, and can we enhance it with detailed information and modeling. So that's a steel program. And then the polymer program, to the point we have certain internal state variable model, but also we run into the molecule area, trying to assemble a large number of molecules and look at stress strain curve and the damage area. So this is eventually going to connect the bridges and doing the design. In fact, some of the composite in the interfacials, you can address numerically what is the interfacial strength by those matrix and the fibers. And on the right side, also the biomaterials start looking to the high rate impact explosive on the brain injury or the lower limbs and so on. So that become another branch of the research. And also look into bio-inspired areas, so design the football helmets and then get the best protection and safety, so on. So those are the 3 branch of material we're working on it. Now, in the magnesium building block, I want to just give you an example in the ICME type of approach. So the top level is internal state variable model, which will carry some of the history, but also because the twinning involved in this alloy, not as aluminum that the 5-slip system and so on, so you have additional twinning going on. So we're working on this very diligently, and the textures. And the blue color or the green color is the new one we're working on it. And the lower scales also working on not only the parts, extrusion, sheet forming, but looking through the dislocation and the molecular dynamics area. And also in the lab experiment, and that's a very critical part in the way that we want to be self-sufficient. We can't rely on the supplier doing certain experiment for us. So in that case, we develop a series of different in-house lab scale experiments in each part of it. And we move on to the casting and recrystallization area ourselves. And finally, we have this demonstration of Mac demo parts project we work with. This is a typical example showing that in the magnesium at certain temperature strain rate, there's a twinning going on, which will exhaust in a way that become a fracture and so on. Then you have the normal stress strain curve. So we're using the crystal plasticity so on to create a yield surface, which will tighten easier with the numerical code for finite element approach. And then in the meantime, the physicists are looking from the dislocation point of view and look at MAG and their interaction with the different elements and see how the stacking fault energy going to impact the SIP system. But also look into, this is working actually with Northwestern, Greg Olson, that their experiment couldn't identify aluminum and also the zinc positions. So we use the DFT to run about 10 different positions of about 1,000 of the numerical simulation to look at what is the most favorable and stable energy location, what is the configuration is of the two different phases. So that get into the design as well as the thermodynamic phase diagram informations. And our optimal goal actually is looking from this area, look into the DFT in the molecular dynamics, and look into the grain boundaries, and eventually crystal plasticity and stress strain curve. We did have some success of pure aluminum, and also we have some success on pure magnesium. So the rest of it is working on the intermetallic and soluble phases and see whether these things can come out easily. And also the other one is in the design, because twinning system, there's a 4 dominant twinning system. And we look at in different design, look in the C/A ratios and see how we can design with a better ductility of the magnesium, which has no rare earth type elements. Rare earths, people been very popular doing that with like cerium and other material. So this is experiments. Basically, I won't show you. The other side will be characterization techniques. This is basically tell you we can cast small pieces. We can quickly doing some sort of deformations, and we can check the grain structures. We can check the extrusion, and then the fatigue and the other things going on with very small scales. So this is basic on, if you can alloy design, you can test these things right in our laboratories, and we can verify what the result is before we can even scale it up to answer any larger parts of the information that sponsor wants to know. So for example, this magnesium front-end project, so we want to predict the mechanical responses at certain conditions. So here has a cast shock tower, like the extrusion lower rails, and has sheet rails, and all this combined together. So basically, you're going to ask your question, can we predict each component, what's the mechanical response based on the processing histories? And then can we put this together with joint, and how that response is under the monotonic and under fatigue loading. So this is the one we finished phase 1 with USM. Basically, we use the cooling rate, indicate porosity, which will be heterogeneity distributed over the different parts. And then we look at the certain boundary condition and see how that response is in the laboratory. It turned out that in a certain way, if you use mechanical analysis, you may find out this is the weak area. Use tomography. We use X-ray tomography. We can scan the whole thing, look at porosity, and it will be weak point here. But once you get boundary conditions, and you analyze it, actually the weak point here is verified in the laboratories that this is the case. So that's kind of encouraging. And for extrusion, I just want to quickly show you what we're doing here. So extrusion, you have this very complicated thin wall type double head we call, and they want to predict these textures around different locations, and they don't relate to the yield strength. So what we do was, in the laboratory, we have to be credible to know how we can predict a described extrusion. So in the laboratory, we designed this laboratory will be maybe 1/10 smaller than this, very small. But you still have a gradient structures.
And then we use the crystal plasticity, including twinning, look at numerical streamline, and including the high temperature stress strain curve. And then we can predict the information, not only the texture around here, but also we want to look at post-forming the yield strengths. And that's what the challenge is. That's what the sponsor put the goal for us, and we go for it. Okay. So this is showing that even in the laboratory, without answer their question, we do our own extrusion, and we look at the twinning and the monotonic twinning at different extrusion ratio, and showing that, yes, the model could do these things. And before we go ahead, describe that thin wall double head type configuration. Again, this is the same thing. In the laboratory, we're doing the very simple sheet forming bending, and we're tracing this local area, similar to extrusion, and then we look at the, even this tension here, we can show some sort of twinning up here. So we trace the streamline of the deformation path and see our model can describe such things. Not only that, we also tracing the, we found out even at 450 Celsius, the material of magnesium, this is the AM30, I believe, will get recrystallized. So there's twinning before the original structure, and twinning going on is the red one, and later on they overcome by the recrystallization. And that's the mechanism, it's a double mechanism compete together. So we have to answer those kind of questions in the laboratory before we really apply to the physical part that USM's asking for. This is also showing the fatigue responses of different cast structures. And the learning from this one is we use one model, we'll be able to produce 3 different products based on microstructure. So this is the plate product, sheet product, and extrude product. And without working with the sponsors, you won't be able to have this kind of data that you can test your model. And finally, there's a joint. The joint is a very interesting one because there are several different types of joints. So we work on the friction spot welding first, and then trying to go back their histories and trying to look at how we can model this joint together, which is a big one for the future research. Even armies are asking for this kind of informations. I just want to quickly give you a cyber infrastructure connection that we have the knowledge management about cyber infrastructures. We have database established, and then we have online calibration of certain tools, and then the model, different scale model in there for sharing basis, but later on we can bring this information out if we need to run it. And finally, this is just started doing this job running on the web. And this is just give example that material and code we put in there. And this is different materials families, from biomaterial to the magnesium to the steel alloy, the one we can get hands on it. Certainly I welcome Brown can be part of this shared data we can share together on this material database, and also different projects. So finally, I just want to say the relevancy to MGI here is several talked before, and now I'm showing this. It's the first principle potentially calculation can relate it to material attributes, and you have to be selective to pick up the right information. Right now, we're working on ductility and creep resistance by the alloy design based on the first principle and other assistants trying to work on. And it has to have a design concept, which may not be created by first principle, but we have to do such thing. And then the multi-scale experimentation is very important because that would be able to quantify some sort of a structure process relationship, and then you can do the validation with it in the laboratory before you claim that you can do the process prediction or product prediction. And we have to have a very close partnership with industrial partners. Otherwise, this MGI program, I don't know how we're going because the community will be very small, just academia effort. And share critical data by the means of cyber infrastructure could be a good way to do it.
And we believe that's the way we want to do it, share with the communities. And then we can all together establish a very broad user base community. That's it. Thank you.
So we have a bit of time for questions, both for Paul and for Mark, if anybody would like to continue the discussion we started earlier. You mentioned first principle computations of utility.
Yes.
How do you do that?
Well, I show you a couple slides, didn't get in detail. There's a magnesium axis over A ratio, and there's 4 dominant twinning system, and there's a square root of 3 of particular dominant system. So we're looking at the profusive single twinning and how that relates to the fracture first, and then come back with computation, say if we insert non-real Earth, but we also compare real Earth like a Syria and model, and see there's a very profusive system and twinning system, and hopefully that will. And the other one is the twin boundary soluble fact. Those 2 areas will work.
So the key is to identify some atomic scale parameters you can compute that initial
Right.
CO, some really basic thing like CO to A ratio. So
So-
hope that correlates.
Yeah, basically you distort the C over A ratio to some extent. That gives you favorable direction that you can calculate.
So then Sears terms calculation.
But the concept is not
Sure.
Just following up on that same question, that you're dealing with magnesium modeling, how do you cope with C plus A dislocations and evolution of texture and the relative importance of the various systems? And what do you do about twinning and critical result shear stress and things like that?
Yeah, well, right now the status, we use the self-consistent crystal plasticity code, and we try to improve that during the dislocation-based form. Homemade type code, we modify it. So if you in extrusion, we can write the Tomei's code with my macroscopic level streamline condition, or you have macroscopic streamline of a sheet or anything. And then you do the decouple analysis using the lower crystal plasticity code we described. Now the physics there still need to improve. So we have another group, material science and physicists, trying to continue to improve. Is this dislocation based or has to be dislocation and twinning based together? So that area, even in the self-consistent flow, we're still improving it. But simultaneously, we're already proving that we can closely describe certain textures and initial yield strength in the moderate extrusion ratio and the sheet form. We can do such things. But then we found out it become very diffusive in the texture when you do the large extrusion that we have dynamic recrystallization. So now we have to look at crystal code, see can we introduce dynamic recrystallization bacteria into the point and how that information can feed into the ISV model. So those are in progress, and we can talk about detail afterwards.
Yeah, it just seems like when you're doing FCC, it's a different story.
Oh, yeah.
When you're doing HCP, with multiple critical result shear stress values.
Yeah. Yeah,
It
because
seems like some critical experiments along the way.
yes, we're doing experiments. So I'm showing we have this, even the macroscopic, you can see the twinning stress strain curve, and they're different. So you have a bit, basal plane and the other plane, your slip system there. So we already implement that information into the model, but still it's not good enough. So we continue to improve that, and then we have a few papers of that we can share with you. But that area, we welcome a lot of people can get active again on that area. Will be very, very beneficial to magnesium. And I believe in the next 2 or 3 years, we can answer ductility questions.
Great.
That's what our goal is. Yeah. Because the computational and experimental tools are about ready. But we also know the gap is, so we focus on the gap, which is the active twinning mode and what is the resolved shear stress, and we quantify numerically, get this in, and how about
enable crystallization at the initial processing condition that impact the product information. So this will come together. And I expect 2 to 3 years we can answer not only that, and also the data issue.
Sure. Question for Mark. You showed the trend line from mild steel usage back in the 50s, 70%, now to 50%, with the use of higher and advanced high-speed steel. Are there technological barriers to take that 50% down to 20%? If I use your number crunching, that results in 20% consider high.
Right, so I mean, it all becomes a business case. So are there hurdles? No, then, right, and there's another sort of aspect of it out there that the term Gen 3 steel is not well defined, but you know, can we get something that is on the order of 1.4 gigapascal or maybe even a little higher, something like 20% elongation, and could we stamp it and not process that actually becomes a question. If we don't use quenching partition or press hardened steels. So there's a lot of opportunity for all sorts of materials at this point in time. You know, other barriers, one is always a business case, and one is you do have to consider, do you actually have a body shop to produce some of these things, and then the integration issues become important.
So the technology gap is in transitioning or translating the flat sheet steel into the final part, through forming and welding.
Yeah, I wouldn't say it's only that. For example, boron-based steels turned out to be unusual for us because it turned out how you actually stamp the part was critically dependent on the rolling direction. That was a unique thing that we didn't know before we went down that road. So none of these are slam dunks, and you have to make sure you understand. And you know, I don't know if we had a material model that's going to show that better than certainly we had an knowledge beforehand. You had to go stamp some parts, and when you make bad parts, you learn. But you know, conceptually, all those things are very cool.
We've exhausted our time.